Okay, I'm kind of digressing here, but I can't seem to help myself. Did a non-sequential timing of the pendulum. Okay, instead of timing every cycle when it passed a certain point. And, if you're a little late with one cycle, you're going to tend to be a little early with the next one. You're going to tend to, if you time too long for this cycle, that means you're a little late clicking when you pass this point. So when you come here and back and get to this point again, if you time it right, you're going to be a little short. So you have non-independent timings if you time sequentially. So here we time non-sequentially. That is, and all I did was I just timed every other cycle, clicking at the beginning and the end of that cycle, but then I'd skip a cycle or even two, and then I'd time again. One thing that motivated this was that when I did sequential timings, my intervals didn't seem to be normally distributed, not to the extent that I would expect them to be for, say, 30 cycles or 30 timings or more. When I did the non-sequential timing of a pendulum length 87 centimeters, the ideal period being 18.65 seconds, that's the ideal if you assume no air resistance, no any other kind of resistance. The mean and standard deviation of the timings that I got for 32 cycles were 1.875 seconds and 0.049 seconds. So that compared pretty well with the ideal, but we don't know what the actual was. There's no way for me to have timed the actual with the kind of timing I did. Although I could time the same pendulum for, say, 100 cycles and divide the total time for 100 cycles by 100 and get a pretty good idea of what the actual was. And I didn't do that for this particular pendulum. In any case, 6 of the intervals were less than z equals -1, meaning on a normal curve, 6 of the intervals were on this side of this point. And 5 of the intervals were for z greater than 1, which means beyond this point being 1 standard deviation above the mean, this point being 1 standard deviation below the mean, which means then that the remaining 21 were within 1 standard deviation of the mean. And that's very consistent with the normal distribution, strikingly more consistent than any of the results I got with sequential timings. Now, sequential timing does give me a very good estimate of the actual period of that pendulum. But, as I have mentioned a couple times, it's not very consistent with a normal distribution. Now, why does this matter? Well, it depends on what you're trying to do. Let's consider. Let's suppose, and I don't have time to do it, I'm not going to do it anytime soon, unless I just can't help myself, but I think I can move on after this. Suppose I timed 32 cycles. Looks like I interposed the L and the C when I wrote cycles. If I timed 32 cycles a large number of times, let's say I repeated that 100 times, that would take me a couple of hours. I'm not going to do that, and then I'd have to do the statistics, but I'd use machinery to do that. So it'd still take me an afternoon to get this kind of result, and it might be worth doing as an illustration. But if I did a large number of 32 interval non-sequential timings, then I would expect those results to be normally distributed about some mean. Now, when I'm timing 32 cycles, I'm going to be closer to the actual time, which is probably pretty close to the ideal time, than I would be on the individual times. Okay, the individual times differ, they have a standard deviation of about 0.05 of a second, 0.05 seconds, just rounding up the 0.049. If I do 32 interval means, I expect that the standard deviation will be less. I expect, in fact, that it'll be less by a factor of 1 over the square root of 32, 1 over the square root of the number of intervals I'm timing. So if I take the standard deviation for individual times and divide that by the square root of the number of observations, number of timings, the number of individual intervals timed, I get 0.009 seconds, and that's a pretty good estimate of the standard deviation that I would expect. Now, this was only one 32 interval timing. I can't infer too much from that, so that 0.009 seconds might actually be 0.007 or 0.011 because I might get a different standard deviation if I did another timing. However, I don't expect my standard deviation to vary a whole lot from 0.049 seconds, so I don't expect this result to deviate a whole lot from 0.009 seconds, maybe 15%. And that's just my intuitive expectation. That could be measured. We could do an experiment to measure just how that works out. So I would expect my 32 interval non-sequential timings to have a standard deviation of only about 1/100th of a second, 0.009 rounded up to 0.01. That's significant. That's significant in interpreting experimental data. I'm not going to go much deeper into that right now, but it's extraordinarily significant. Another very significant thing to understand about experimental data is that if I'm doing the timing, then I have a neurological bias to either time things short or long, and there's nothing I can do about that bias. If I try to compensate for it, I'm going to end up with much bigger standard deviations, and my bias will get biased. It's going to mess things up terribly if I try to compensate. So I just do my honest best to get the timing right. But in doing that, I can't control it. My brain and the neural system that connects my brain to the finger that does the clicking or the timing is inherently going to be biased. There might be a psychological aspect of that, and that's true of everybody. Everybody is going to have a mean, an actual mean in timing something like this that's going to differ from the actual in one way or another. Now there are other, in trying to get to the bottom of exactly what this pendulum is doing, there are minor factors also that cause the actual to deviate from the ideal. As I say, I can do a long timing. I could time 1,000 cycles. I could do it electronically and see just what kind of deviation the actual time seems to have from the ideal. Now, another question then is that comes up just from this data, okay, based on this one 32 interval sample where I got this mean, what is the probability that my bias causes high readings? Because this is slightly higher than the ideal, and it's slightly higher than the actual when you measure the actual over a large number of cycles. So what evidence is there that I tend to measure high? I tend to measure the intervals a little bit longer than they actually are. I'll come back to that and talk about that briefly in one hopefully brief subsequent video.